Hey, hello there. Let's talk about today's Leetcoding challenge question. Find minimum in a rotated sorted array 2. Suppose that we have an array that's sorted in the ascending order, and now this array has been rotated around some pivot point that's unknown to us. Looking at the concrete example array, this is the original array that's sorted in the ascending order, 0, 1, 2, 4, 5, 6, 7. This array has been pivoted, rotated around this pivot point, the position in between 2 and 4. So we're cutting the array into two halves. The first half is 0, 1, 2, and move that part towards the end. So the rotated sorted array becomes 4, 5, 6, 7, 0, 1, 2. So in terms of the ordering of the elements inside this rotated sorted array, it's ascending a sudden job and then going back to ascending order as well again. Now the question asks us to find the minimum elements inside this array. One notice that there may potentially be duplicates inside this array. This is the only thing that set this question apart from the prior question, find minimum in a rotated sorted array. So in that question, there is no duplicate. The case is relatively simpler. So let's talk about how we find minimum element inside any kind of array. Let's not assume any kind of a sorted order about the array, and we want to find the minimum elements. We have to look at all the elements at least once and remember what is the smallest one that we see. So it's going to be a linear time algorithm. Just pass through all the elements inside a array where we don't assume any kind of a sorted order. So that's linear time. If the array is perfectly sorted, in this case, as is the original array, then the minimum number is going to be the first element inside this array. So it's going to just be a constant time looking up at the value. Now this array is rotated sorted, so it's not fully sorted, but it's not totally unordered. So this is in between unsorted and sorted. So the algorithm that we are looking at should have a runtime that's in between constant time and linear time. So that's leave us to logarithmic time. So find a value inside array in logarithmic time. It's pretty clear. We're looking at binary search. So the big idea behind binary search is that we're looking at the three numbers. The lower bound, the upper bound, and some medium pivot number. And based on those three pieces of information, we want to decide which half of the problem we can safely disregard and zoom into the other half of the problem to find the answer. So here we are looking at how we compare the array's number elements indicated by those three pivot, lower bound, upper bound, and median points, to figure out where should the minimum number resides, and use that to iteratively or recursively, whatever, repeatedly reduce the size of problem until we find the minimum, so that we can lead to logarithmic time. So let's look at let's just look at this one by one. The first case is that let's just talk about this graph a little bit. Now, assuming that we have an array and using the x-axis to indicating the array's index and the y-axis to indicate the element's value. So because this rotated sorted, it's increasing a certain job and then going back to increasing again. Note that the upper bound should never be higher than the left point, because if this is higher than the left point, it's not really a cutoff and move over. That will violate the prior property of a sorted array, so it has to be in this kind of shape. Now, the first case is that when we use the three number to partition the array, basically rotated sorted array into two halves by the lower bound, upper bound, and the median pivot position. If it's the first case here, we can see that the left part, the part that's between these two lines here, it's strictly sorted in the ascending order, and there's no way that the minimum is in this part, because the job, the minimum number is always the starting point after this job here. So just based on the relatively relationship between this three number, or this two number in particular, we can identify that we want to continue looking into this portion, this half of the rotated sorted array, to find this minimum. So just in summary, if we find the median value is larger than the upper bound position's value, that means the right hand side partition of the rotated sorted array contains the minimum, and we want to basically only considering that part. So we can update this by moving the median value to be actually one larger than the median, because to have this they are rotated. To have this median value to be strictly larger than the upper bound's position value, that means the job hasn't happened yet. So we can safely move it to be one more than that. So this is the update rule for the first case in the binary search. Okay, let's go back to that and grab the second case and talk about that. So this is the second case when we have this kind of partition with the 3-number partition, lower bound, upper bound, and the median part. We can see that the left-hand side is a rotated sorted array. That's why the median and the minimum number has to be in that part. So we can safely disregard the upper bound part. This condition, this kind of partition is indicated by that the median value, median position value is smaller, strictly smaller than the upper bound's value. But that doesn't exclude the case where this median value is pointing at the true minimum, so that we don't want to overshoot. So the update rule for the upper bound in this particular case, we just set it to be median position, because that one has the potential to be the true minimum. So that's the second case. The very last case, the very last case is the tie. That would never happen if there is no duplicates. If we find that the median value, median position value, and the upper bound position value has the same value, that's only possible when there are duplicates. And actually there are two possible scenarios. One is that the duplicates extending from some prior part in the left hand side and just left the left portion between low and median. If that go extending through that, then we want to really zoom into this part. The other case is the same value is extending through median towards upper bound. Then the part that we would want to zoom in is this left-hand side part. So just based on this two values relationship, there's no way that we can determine which part of the array we want to disregard. So the only thing we can safely do is to just decrease the upper bound by 1. So that moves also move the median value towards left by a little bit, and hopefully after a few updates we can, as in this case, we can see that it's already in the dropping part. So doing a few updates, we can resume this cutting half and cutting half operation. Like here, if we drop it here, then we're pretty sure that the right hand side is the part we want to keep, and we can resume the binary search. So yeah, so just in short, when there is the tie, we can no longer do binary search. All we can do is to do a linear update of the upper bound by decrease that by 1. So that's the 3 cases. Yeah, so let's go back to the code editor and code up the solution. It's relatively simple. Once we can have those 3 scenarios in our mind, the code is pretty simple. So the lower bound and upper bound are the first position and the last position in the array, and the termination criteria is that the 2 bonds haven't converged into one point, so we haven't successfully identified the single minimum number inside this array. We want to repeatedly finding the median position, which is just this 2 add together and divide by 2. And now is the 3 cases. We want to test whether this position is less than or what's my first case? It's larger than upper bound. If it's larger than the upper bound, then what I would do is to increase the lower bound to be n plus 1. The other case is that it's strictly less than the upper bound's position's value. That means the median position have a potential to be the true minimum. If it's not, then the left partition of the array has to be rotated sorted. So we want to keep searching that part. The only last case is that it's a tie. If it's a tie, then we are not sure which part we can safely cut off. So we just reduce the upper bound by 1. In the end, the two bonds, lower bound and upper bound, will be the same value. So we can either return the number at high or low. They are the same position. So that's the code for this problem. And so in the worst case, when the array is just the same number repeating itself over and over and over and over again, this will converge after we decrease h from the last number towards 0. So that's the only case when this will break. So in that case, the time complexity will be linear time, because we, from the right hand side, and move that one at a time to be the left side. So it's the worst case, it's linear. So when there is no duplicate, and out of n, when worst case. Every element when we just have the same number. So that's the time complexity for this problem. And because it's binary search, all we have is the 3 positions, so it's a constant space problem. For the prior question, because it's just it's basically just getting rid of this case. So the code is just that. So we have two branches inside this code, binary search code. For this 153. In the rotated sorted array, in the case there's no duplicate, it's guaranteed to be in log time. Yeah, all right. So that's this question, and it's a prior question today. Binary search.